Thanks, Animesh. Hello, everyone. I'm Abhinav Valada. I will be chairing this session 6 on perception. Today, we have 3 very interesting papers. Before that, if you have any questions during the talk, please post them in the Q&A and I will read them out after the talk. The first presenter today will be Martina Zambelli from DeepMind, who will present their work on learning rich touch representations through cross-modal self-supervision. With that, Martina, please go ahead.
Hi, I think you can see my screen. My name is Martina Zambelli. I'm a researcher at DeepMind, and today I'm presenting a work done in collaboration with Yusuf Aitar, Francesco Visin, Yushan Zhu, and Raya Hatzel, titled Learning Rich Touch Representations Through Cross-Modal Self-Supervision. The sense of touch is quite important in several manipulation tasks that we perform every day. However, it is still rarely used in robot manipulation. In this work, we focus on learning touch representations without supervision, leveraging cross-modal correlations, and with the objective of training features that can potentially enhance robot manipulation skills. So lately, self-supervision has seen great advances in several domains. Vision, for example, with SimClear and CPC, language with GPT-3, BERT, and transformers, and sound with SoundNet and XDC, for example. In all these domains, large datasets were available and fostered research in these fields, together with advanced learning algorithms. However, less progress was made using the tactile modality. So we contribute to this field by introducing 2 datasets collected with a simulated shadow hand and that contain multimodal data, which include also the sense of touch. And we also propose a learning pipeline to learn rich touch features using cross-modal self-supervision. So let me start by our motivation. Why is it that touch is actually quite interesting for us? Well, on several occasions, vision is not available. For example, if you're looking for a set of keys in your pocket or in a bag, vision is not the sensory modality that you're relying on. Another example is switching gears in a car. You're not actually looking at the gear shift as your attention is possibly on the road. In all these situations, touch becomes very important. And in doing these tasks, a mental model of the object of interest is still available to us. On the other hand, touch is still quite underutilized in robotics. And we believe this is very relevant in robot manipulation in particular, where occlusions and limited visual capabilities are likely to happen. In fact, the moment the robot grippers or fingers grasp an object, at least part of that objects are not visible anymore. So we argue that vision alone may not be sufficient for dexterous manipulation tasks, and that cross-modal representations can enhance robot manipulation skills. Just to give an overview of our work, so we collected data from a simulated shadow hand interacting with several different objects. We collected multimodal data that comprise vision, touch, and proprioception, together with other information such as actions, objects, IDs, and reward. The learning approach that we put in place relies on 2 steps. The first one is a pre-training step, where we pre-train a representation for touch features using cross-modal losses without giving any supervision. The second step is the evaluation, where we evaluated the learned features on few-shot object classification and pose estimation. I will now describe the dataset and then the learning pipeline that we propose. So, as I mentioned, one of the contributions of this work is the release of 2 datasets, which we use to train our touch representations. To collect this data, we ran a maximum a posteriori policy optimization algorithm, an MPO reinforcement learning agent, to control the hand movements. The agent was blind and rewarded by contacts between fingertips and objects, while it did not receive any classification scores that, as you see in the next slide, we use for feature evaluations only. We collected 2 datasets, one using YCB objects, as shown in the first row of these videos, and one using props of different shapes and sizes that are shown in the second row of videos. YCB objects are everyday objects and belong to an externally available dataset that is often used for benchmarking manipulation tasks as well as computer vision methods. For props, we generated objects in MuJoCo, defining their shapes from simple primitives such as boxes, ellipsoids, or sphere, for example. We sample different sizes, and importantly, we define them to be either rigid objects or deformable objects. For YCB objects, we change the orientation for each object, and this allows us to evaluate features also for pose estimation, while props were kept fixed. For props, in fact, the complexity of this data set is provided by the different texture, that is the softness of some objects. So let me now go through the learning pipeline, starting from the first step, the pre-training step. To learn touch features, we exploit naturally existing correlations between touch, proprioception, and vision. The learning architecture is shown in this diagram, and I'm now going to break it down and take you to all its parts. Starting from vision. So each visual frame is processed through a convolutional encoder. Then touch and proprioception are processed through an MLP and an LSTM. And here memory is quite important as it captures dynamics information from these modalities over several time steps. Touch features are then learned using cross-modal self-supervision. To do so, we use different methods, including L3net or time-contrastive networks, cross-modal distance classification, as well as variants of contrastive predictive coding. So in the following slides, I will briefly mention these methods, but I'd like to refer you to the paper for all the details. So L3net stands for Look, Listen, and Learn by Rantilovic and Zisserman, and is based on binary classification of temporal sync and non-sync pairs. This approach was developed initially for vision and sound, but we adapted it to our contexts to model vision and touch. Then CMDC, cross-modal distance classification, proposed by Yusuf Aitar et al. In 2018, is based on predicting the temporal distance between given cross-modal pairs. TCN, time-contrastive networks from Sermonet et al. And contrastive multi-view coding from Tian et al. Are both based on contrastive losses and look at similarities between sync pairs across different camera views. Again, we adapted these methods to our context to model vision and touch. Contrastive predictive coding by Van de Orde et al. Predicts future latent observations using the current latents and previous contexts. We implemented a cross-modal version of this algorithm where touch features predict vision. In this diagram, you have an overview, an intuition of how the cross-modal CPC would work. And in addition to the cross-modal version that predicts the future, we also evaluated another variant where we predict the history and the current state as well. Finally, we evaluated also a cross-modal generation method to generate one modality, that is vision, from another one, touch. This method has been used in several works and is presented here. So here the decoder reconstructs the visual input and the generation loss is then used to train the touch features. Then the second step of the pipeline is the evaluation step. We evaluated the learned features on few-shot classification and pose estimation using an LSTM and an MLP to generate labels from features. Here we learn few-shot classifiers on top of pre-trained touch representations, fine-tuning the entire touch model end-to-end. I'm now going to tell you a bit more about few-shot classification and the experimental results. For few-shot object classification, we evaluated each method on increasing number of samples. That is showing only a few examples for each category or object class. And also we compare it with learning from raw data or from scratch. We first evaluated on few-shot classification on objects from the same dataset, both on the props dataset and on the YCB objects dataset. In this slide, you can see accuracy scores for props on the left and YCB objects on the right. Cross-modal generation here achieved the best accuracy on few-shot object classification, achieving a 25% gain compared to learning from scratch. Other methods, based on contrastive losses, for example, showed comparable performance on average, and these results hold true qualitatively for both datasets. Then we also evaluated learned features on unseen data, I'm showing here the results obtained for cross dataset experiment, where we trained features on one dataset and then we evaluated them on the other datasets. For example, training on props and evaluating on YCB and vice versa. These plots are a bit dense, but what I wanted to notice here is that here contrastive methods perform the best. They are still better than learning from scratch, and interestingly outperform cross-model generation, which is based on visual reconstruction and is now the worst performing one, as it is actually overfitting to the specific dataset it was trained on. Finally, the learned features also improve the Pos estimation accuracy. These slides show the accuracy scores for Pos estimation on the YCB objects dataset, which is a dataset where objects were changing the pose during data collection. Pose estimation is posed here as a classification problem again, where each pose corresponds to one class. The scores here are the average obtained across all the objects. So now discriminating orientation or poses from vision is quite hard, and cross-model generation doesn't provide robust features in this case either. On the other hand, contrastive methods perform better in this more complex task again. To summarize, we propose a pipeline to learn touch features using cross-model self-supervision. We compared several existing methods and cross-model variants, and we evaluated the learned features on few-shot object classification and pose estimation, finding that contrastive methods perform better on more complex tasks. Finally, we also released 2 datasets, and we hope to foster more research in this field. So with this, I would like to thank you for your attention, and I'm happy to take any question. Thank you very much.
Thank you, Martina. We have one question in the Q&A. How do you think about bridging the gap between the synthetic touch data and the real-world touch data?
This is a very interesting question, especially because touch is quite hard to simulate at the moment. And the model that we have at the moment are quite different. So with this approach, we are not planning to give a solution for bridging the sim to real gap. However, our architecture is agnostic of the source of data, which means that we are confident that the learning pipeline that we are proposing can actually work with real sensor data as well. And we are actually keen to try that as future steps in our project.
All right, thank you very much. Okay, in the interest of time, I guess we can move on. Thanks again.
Thank you.
So the next talk would be by William Agnew from University of Washington, who would present their work on A-modal 3D reconstruction for robotic manipulation via stability and connectivity. With that, William, please go ahead.
Hello, everyone. My name is William Agnew. I use he, him pronouns, and I'm a PhD student in the University of Washington. I'm presenting my paper, A-modal 3D reconstruction for robotic manipulation via stability and connectivity. We aspire to enable robots to manipulate novel objects in novel ways in complex and cluttered environments. Below, you can see several cluttered and messy scenes that are definitely not from my clean and organized apartment. In these scenes, there are a variety of containers that can be emptied. There are shoes that can be deformed. There are fruits which can grow and ripen in different ways, all different novel objects that are impossible to anticipate until the robot encounters them. There are several existing solutions to manipulating these objects in different ways. One class of solutions are model-free methods like model-free RL. These methods will take many different samples or demonstrations or experiments with these objects for a while, and then learn a policy to be able to manipulate specific objects in specific ways. However, quickly generalizing to novel objects or novel manipulations is still an active area of research for these methods. Another class of solutions are model-based methods like model-based RL or MPPI. These methods will use a model of the environment often a 3D simulation of the environment complete with 3D models, to learn a policy or plan a directory, and then at a high level, transfer it to the real world. However, it's quite challenging to quickly get models for novel objects. You can't simply look up the object in a database or send it to a human CAD designer to spend several hours creating a model. You need to be able to very quickly get a good 3D model of the object to be able to use it in your simulation for learning. And that's the problem that this project really looks at addressing. So we investigate using a recent tool that has gotten very powerful in computer vision, 3D reconstruction deep neural networks. And these deep neural networks, what they do is they'll take an RGBD image of the scene and instance segmentations, and from that estimate complete 3D models of all the objects in the scene. And the big difference between these and traditional SLAM methods is that they will estimate parts of the object that are occluded or off camera or self-occluded. And so really produce a complete model from a single image. So in theory, if your 3D reconstruction neural network is good enough, then from a single image, you can get a very accurate object model, which is quite exciting. So what we did is we took one of the state-of-the-art unseen reconstruction networks genre, and we used it to reconstruct the objects you see in the scene on the left to create the simulation you see in the right. And then we used an MPPI planner to make a trajectory using the simulation, and then we transferred it back to the ground truth scene on the left. And what we found is that unfortunately the reconstructions from the state-of-the-art planner tend to fail. So the big reason that these reconstructions tend to fail is that they're unstable. They will roll away, they will topple, shift, or otherwise move in simulation, rendering the simulation a very inaccurate model of the world and making the planes not transfer back very well. So as you can see, the pink cereal box on the left that we can reconstruct on the right here just immediately topples over and the robot isn't able to successfully grab it. Really impact the performance of these reconstruction networks. So here, the orange lemonade container immediately topples over in the reconstruction because it's just reconstructed without a base because the base is off camera. And similarly, this orange vase also immediately topples over because its base is occluded by the orange lemonade container, and so isn't reconstructed by the baseline. So after thinking about these problems for a little bit, we came up with kind of the key insight of this project. And the key insight is physics should optimize for physical and dynamic fidelity and not just visual fidelity. And this may seem rather obvious to us as roboticists, but all these existing 3D reconstruction networks optimize for things like chamfer distance, which are really metrics of visual fidelity. But as we know, we want these models, or we want the models that let us plan successful manipulations and not the models that look good. So in this project, we looked at embedding different physical priors into the 3D reconstruction networks to make them produce objects with more realistic physical behavior. So specifically, we embedded stability priors and connectivity priors. So before I go into more, a quick note on the output of these reconstruction networks. So the reconstruction network outputs a 128 cubed voxel grid, and each voxel has an occupancy probability that says if the voxel will be on or not in the object. So you can think of the reconstruction network as outputting a probability distribution over possible objects. And typically, we just set all voxels with a probability of greater than 1/2 to existing and less than to not to obtain our object. For a stability objective, we want to reconstruct objects where the center of mass of the object is within the base of support of the object, so it won't topple over. So what we did in our paper, given an object defined by these occupancy probabilities, we calculated the chance that an object sampled from this distribution is stable. And then we find a differentiable approximation for this probability. And we actually use this as an additional loss function when training our 3D reconstruction neural network. So as you can see, when we add our stability objective in this toy example, the probability of this base existing becomes much higher. The other important thing to note is that this stability objective complements the existing shape prior. So we're not simply like projecting or extruding the object down to the table. We're amplifying specific parts of the shape prior to reconstruct an object that's both likely to exist and matches the observations, but is also stable. However, so when we apply this to our reconstruction, so on the left is the robot view, and you can see our baseline really only reconstructs the top part of the object that's visible. However, when we add our stability objective, we reconstruct the base, and we also reconstruct a bit more of the object because we are amplifying the shape prior. But we're still far from a good reconstruction. Notably, we're missing the middle of the object here. So if the robot tries to grasp the object, the hand could just go through this void in the object and cause the planning to fail. To fix this, we introduced a connectivity objective. So given an object distribution defined by these occupancy probabilities, we calculate the chance that a sampled object is connected. That is, there's a path from every on voxel to every other on voxel. And we found a differentiable approximation for it. And we also use this as an additional loss function when training our 3D network. So when we add this connectivity objective here on the left, we kind of fill in this void or this gap in the object and the inferred base. So as you can see, when we add our connectivity objective to our stability objective here, we infer the rest of the object. And importantly, we kind of keep this triangular shape of the wine glass, showing that these two objectives are really just complementing the existing shape prior and amplifying parts of it to achieve these physical probabilities or physical properties. So here's another overview of our system. We take in a single image observation of the environment. We use an instance segmentation network, UOS, to segment every object. And then we pass these segments through our 3D shape estimation network to get per object models. And after some post-processing, we get a reconstruction of our scene. We then apply MPPI planning to compute a trajectory in the simulation. And then we transfer that trajectory back to the ground truth and execute it to determine whether we succeed in our task or not. To test this, we first developed a 3D reconstruction dataset of around 1 million cluttered reconstruction instances of ShapeNet objects stacked, leaning, and piled with varying levels of occlusion and varying types of support and stability, so quite complex. We found that our system genre improved the reconstruction quality as measured by chamfer distance by 28%, and furthermore, it more greatly improved the reconstruction quality on more highly occluded objects, as seen on this graph here. So here are some more qualitative results. So the baseline really misses the occluded portions of the object, but ARM successfully infers both a base and a lot of the included portions here. However, the real evaluation of a 3D reconstruction system is how well the models allow a robot to plan in simulation and transfer back to real. So we made a benchmark of about 2,500 different robotic manipulation tasks in occluded settings with YCB and downloaded object models with pushing, rearrangement, and grasping tasks. We found that planning using ARM reconstructions improves the task success rate by 42% over the baseline. So here are some qualitative results. So as you can see, ARM in the middle, the reconstructions are stable, and the robot is able to successfully grasp the object in simulation and then transfer the trajectory to real to successfully grasp it back in the real. Whereas the baseline genre, the objects are unstable and the robot is unable to successfully plan a trajectory and transfer it back to real. We also found that our system ARM is robust to very high levels of occlusion. The baseline performance drops by about 80% from no occlusion to 90% occlusion, whereas ARM performance drops only about 20% from no occlusion to 90% occlusion of the target object. So in conclusion, we embedded physics priors into 3D reconstruction to improve robot performance with the reconstructed models. But our cluttered reconstruction robotics manipulation benchmarks are still quite challenging. So we have released them on GitHub, and we encourage further research into this area. Specifically, we only embedded a couple of physics priors into our reconstruction, and we would like to see future work that connects reconstruction directly to the physics model to be able to directly optimize shape to match dynamics. Thank you. Any questions?
Thank you, William. There's a question in the Q&A. How did the algorithm avoid classifying multiple objects as a single object, which would be problematic in stability and connectivity constraints, such as in cluttered environments, it might be difficult to determine where one object ends and the other could begin?
Yes, so that's definitely a challenging problem. In this work, we limited ourselves to the reconstructions and not focusing so much on the segmentations. But it's definitely an interesting problem to think about. Could you have the robot interact with the scene a little bit to kind of infer like which things are objects and which things are the same object? Excellent question. Yeah, it would be nice to see more work on segmentation in cluttered environments.
Okay. I have a question. So what are the typical voxel sizes do you use, and how does this influence the reconstruction?
Yeah, so the voxel sizes are dependent on the size of the input point cloud, so the size of the point cloud we observe. So basically, we take the maximal extents of the point cloud and double that, and then divide it into a 128 cubed grid. Obviously, at some point, this voxel resolution will affect manipulation, especially if you're doing fine-grained stuff. But honestly, reconstruction in these cluttered environments is just so challenging that isn't really impacting performance yet.
Okay, thank you so much. All right, so let's move on to the last talk. The next talk is by Louise Z from Carnegie Mellon University, who will present their work on multi-resolution graph neural networks for segmenting large-scale point clouds. William, can you stop screen sharing, please? Yeah. Okay.
Yeah, that's okay. I can wait a bit.
Apologies, Zoom crashed on me and I had to exit and rejoin.
Yeah, it's
Okay.
fine now.
Oh, actually, let me adjust the sharing. Are you guys seeing the presenter view, or is it the?
No, I can see the main view. That was perfect.
Main view? Okay, yeah. I'll do it again. All right. Okay, so hi, everyone. I am Louise. I'm a master's student at CMU. Today, I'm going to present our work, MAGNET, a multi-resolution graph neural network for segmenting large-scale point clouds. This is a joint work with my advisors Tomotake Furuhata and Kenji Shimada. In the following presentation, I'm going to demonstrate its qualitative results, and also its ability to process large-scale point cloud scans. In the recent years, there has been an increasing number of high-quality 3D sensors being invented. These sensors have made it possible to obtain high-resolution point cloud scans. There has since been an emerging demand for 3D perception algorithm in many industries. For example, point clouds generated from high-precision 3D scanner to measure distances to objects are now being used for automated site inspection. And for this automated site inspection tasks, there always requires a semantic segmentation algorithm to identify instances from a point cloud. This is also the case for autonomous driving, because the object detection in 3D perception is an essential component to provide depth information and to ensure the driving safety. For the challenges, there are mainly 3 challenges for point cloud semantic segmentation currently. For point cloud segmentation, we are typically given a large quantity of point cloud scans generated from 3D sensors like LiDAR and time-of-flight sensors. And each scan usually contains millions of points with XYZ and RGB information, or sometimes intensity specified for each point. And the semantic segmentation, what it does is to locate the objects of interest by identifying the points that belong to each instance in an environment. And looking at each point alone doesn't typically give much semantic meaning enough to determine a points class with the basic XYZ and RGB information. And in this case, neural network is also necessary because the semantic class cannot be extrapolated for each point with traditional segmentation techniques like region growing and model fitting. Secondly, we also want to be able to maximize the use of computation resources and process multiple point cloud scans at once, ideally on a portable device. In construction applications, this is especially important because the algorithm needs to efficiently handle point cloud scans of buildings with many floors without posing delay. And thirdly, depending on the sensor type, point cloud's density distribution can also vary from region to region in a single scan. This poses additional challenge to extract semantic information uniformly from point clouds. The existing solutions to typically deal with a large quantity of point cloud data is to slice the whole space into cubes of a certain size. But this approach disturbs the integrity of data, however. A single object can potentially be sliced into different cubes, and the sliced partial point cloud can be topologically similar to other objects. This naturally leads to confusion in prediction, while it's also possible to slice into larger cubes to retain topology as much as possible. The larger cubes can lead to longer inference time and additional computation cost. The trade-off between segmentation accuracy and computation cost poses a dilemma to the current approaches. And with a goal to propose a solution for large-scale point cloud segmentation, we have divided the segmentation process into 2 subtasks. With a raw point cloud scan from 3D scanners or other 3D sensors, we first form point clusters based on each point's geometric features to reduce computation costs for the subsequent segmentation processes. We then feed the point clusters forming to a graph into a node classification network that assigns a label to each point cluster. And to be specific, for the cluster forming algorithm, we first convert the large-scale point clouds into semantically similar point clusters with supervised clustering approach. The algorithm first standardizes the point cloud with point-net transformer and then use a generalized minimal partition equation to optimize and produce semantically similar clusters. Then the edges of the graph are embedded with 13 edge features between connected neighbors. And by doing this, the amount of GPU memory demanded by the subsequent node classification network is drastically reduced. After the graph has been formed, following the construction of the graph, we then move on to assign features to each node in the graph, essentially the cluster features. Our proposed framework has a multi-resolution cluster feature extractor network. This network reasons the relationship among points in a cluster at different resolutions, and then max pulls the feature vectors at different resolutions to retain the transformation invariant features. We have observed that the concatenated features from different resolutions can provide richer feature representation compared to the resultant features from the final convolution layer alone and lead to better accuracy results in the node classification task. After the clusters have been embedded with its respective features, at this stage, the clusters have been formed, the relationship have been defined, and the cluster features have been assigned to each of the clusters. Now we can move on to perform the node classification. The node classifier defines which class each cluster belongs to. And as a high-level introduction to the node classifier network, the network is built with graph convolutions, and the residual connections in the network can provide high information density through layers. The backward fusion network beside the backbone then further enriches the representation with the backward pass. And during training, we have used the cosine annealing technique to find the best hyperparameter. As a more detailed view of the backbone, it takes in a graph G where it contains n number of nodes. And for each of the node, it essentially represents a cluster that we formed previously. Each of the nodes also features the node features that we derived in the cluster embedding network. And each of the nodes essentially takes in, essentially passes its information through the backbone. And the backbone is constructed using residual graph convolution blocks. The outputs from each convolution level are fed into the backward pass after the backbone layers. And at the end of the backbone, the features from different convolution level are concatenated for prediction network. So after we have the nodes gone through the backbone layers, the backward fusion network then further enriches the representations. The network takes in input from the backbone GCN, and when it fuses graph features, the network is designed to produce a constant number of features at different level, because upsampling operations in graph convolution neural network are insufficiently supported by the current literatures. And in the unweighted formulation of our backward pass, the features are concatenated between layers prior to the convolution. And because the manual assignment of importance can potentially induce bias from human knowledge, so we further introduce a set of learnable weights in opposed to naive concatenation in the unweighted formulation. So in order to validate our network's performance, we have used different benchmarking data sets. To test its performance for large-scale indoor segmentation tasks, we're using Stanford large-scale 3D indoor spaces dataset. In the dataset, it contains 13 object classes common to indoor scenarios, and each of the room has on average 2.6 million points, and there are in total 270 rooms. For evaluation metric, we're using overall accuracy and intersection over union. The overall accuracy is a point-wise accuracy calculated among all points in the room, and the intersection over union is calculated for all objects in the room and averaged over all rooms. All of the reported tests are obtained with standard 6-fold cross-validation protocols for all of our texts. For our test for the Stanford indoor spaces data set, we have calculated the performance for all areas and compared to other models for overall accuracy and average IOU. It has been shown that our model can outperform the current models, and this proves our model's ability to capture semantic information from large-scale point clouds. And to further test our performance for outdoor scans, we are using the virtual kitty dataset. The network is also trained without RGB information to test our network's ability to learn purely from geometric information, because RGB is sometimes missing from the scans. Our performance is again calculated for all classes and compared to all of the other models benchmarked for a virtual kitty dataset without RGB information. And this has demonstrated our network's ability to capture geometric information, even when color information are not available. Further, we have tested our network's ability to inference multiple point cloud scans on a commonly available 11 GB GPU. It can be observed that with an increase of room number, the increase in memory usage slows down and resembles a pseudo-logistic growth. Our model scales nicely with an increased number of scans to be processed and would be desirable for applications where a multitude of dense scans need to be processed. While it is showing a lot of merits, our model still carries several limitations. We have found that the model mainly presents 4 failure modes, and they are shown for the window classes. There are mainly just over segmentation, incomplete segmentation, residual segmentation, and misidentification of points. One probable cause of the failure is that the change of lighting or insufficiently differentiable lighting scenario in the point cloud. And another probable cause that we speculate is because of insufficiently generalizable training samples that we have. In conclusion, our network, MUGNet, can efficiently handle large-scale point clouds when coupled with existing clustering techniques. And our MUGNet is an effective graph neural network framework that captures point cloud topology. And for future work, we're looking to establish stable applications in site inspection and compliance verifications with high-level probabilistic reasoning. Our code will be released via GitHub soon, and our interactive session is at 12:30 to 1 p.m. If you have any questions, please feel free to email me. Thank you.
All right, thanks, Louise. I have a question. So does the GPU memory and time consumption that you reported here, does it include the clustering pre-processing time?
So for that one, the time is not, the timing that we reported does not include the pre-processing time, but for the GPU consumption, it has been included.
Okay. Maybe another question. Did you evaluate with different types of clustering methods, like unsupervised methods, for example?
Yeah, we actually did. So we first tried with naive like model, like region growing technique, but for the region growing technique is pretty limited by the RGB information. For example, for like LiDAR scans, when it doesn't have any RGB, it will be highly affected. And there are always some kind of mixed classes within each of the clusters. This is also present when the RGB information is in the loop. So I guess after we tried the unsupervised versions, we have realized that those features are typically not like that. Those methods are typically not robust to the classes because, for example, boards and windows, they typically have very similar geometric features. However, those are very hard to be differentiated if we don't have the RGB information. So after that, we have moved on to using a supervised approach. Yeah, but I guess the supervised approach still has some places that can be modified or tuned. We just haven't really focused on that because it has provided us with relatively unified kind of clusters.
All right. Thank you very much. And thanks to all the speakers again. I believe we have a 10-minute break that follows.